so much for having me. I mean, this is really exciting. You know, John and I talked a little bit about this earlier, but and this gives you a chance to sort of date where I come from. But you know, I was one of the people who helped this ecological economics off the ground in the 1980s, and so this has come a long way, and it's exciting to now sort of come to the hub of where, if it's not yet happening, where it will happen. So I want to thank you for the invitation. I did want to start my talk with a brief quote that some of you might have heard from Lawrence Peter Berra, who some of you know under the name Yogi Berra, who observed quite well that in theory there is no difference between theory and practice, but in practice there is. After a quick sort of case study illustrating one of these aspects, I want to come back, sort of broaden this out to think with you then ultimately also a little bit more about the broader sustainability challenges and the role the university and the Gandhi Institute might have in all of this, especially as you are developing spires that deal with food, that deal with agricultural issues, that deal with health issues, that deal with sort of the complexity of all kinds of human environment and other kinds of interaction. So where to position oneself in that emerging dynamic, if you wish. So I did start out as an economist, and that's why one of these circles is a little heavier than the others. But it's an obvious recognition that the economy, as we so often say, is a part of a subsystem, basically, of the ecosystem, that we interact with this through use of materials and energy and release of waste products and the like, and through this then influence dynamics in ecosystems that then can feed back to influence the economy. So we know all of this, right? On a very fundamental, sort of theoretical level, much of the way in which we develop models in economics and ecology actually mirrors insights from and methods and techniques developed in engineering sciences and in physics. So that holds for both of these disciplines, and that hasn't really changed to some extent in the last 20 or 30 years, where we're now doing disequilibrium or non-equilibrium thermodynamics that in new ways now sheds light on the emergence of new properties in these fairly complex systems. So that's sort of where I come from, and most of my work, and Bob Herendeen knows this from the really early days. So I was trying to zero in on the middle section of this Venn diagram, but increasingly sort of also moved into the other directions. As that movement sort of has happened, there is sort of the substantive set of questions that I've increasingly been concerned with is, how do you understand systems that are really complex? And given that baggage that I bring to this, I perceive this as not a question, the understanding of complex systems, not a question that can be answered from any one particular discipline, be it economics or biology, or you name it. You really need this multidisciplinary perspective, and with the limited tool set that I have, I sort of limited myself to sort of 3 disciplines. And there are many others, obviously, one would want to bring into this. But from a practical perspective, what I'm really also interested in is that as we try to influence the dynamic of these complex systems, be it an industrial system, be it a region, as we try to influence this, we sort of turn the levers, we turn the knobs, and then oftentimes, if we do this right, we see sort of the desired output of some of these actions that we carry through, but in many cases there are all kinds of unforeseen consequences. And wouldn't it be cool to know a priori roughly what those would be, which directions we move those systems? And so a lot of the work in the last 15, 20 years I've done was really then trying to bring sort of a systems perspective and a dynamic modeling perspective to better understand some of these ripple effects, some of these ramifications of these system interventions. So that's one sort of set of comments of intellectually where I come from. The other set of comments, and ultimately, obviously, is that these systems, infringe on and are constrained by all kinds of other common boundary constraints, biophysical constraints, but also moral and ethical issues that constrain sort of the solution space for our activities, and legal and institutional setup that really determines what we can or cannot do. What's really interesting is that these constraints really also do change with time, and we try to change them through time, and I'll come back to this later, but take the case of climate change. I mean, it really typically means a constraining of the biophysical space within which we can operate. And then on the legal and institutional front, we try to develop tradable permit systems, we're trying to develop renewable portfolio standards, which are really efforts, if you wish, to increase the realm of economic activity within this tightening space that now sort of gets driven to some extent by climate change. And so, at least to some extent, with some of the work we're doing, we're trying also to influence this, and which is actually sort of the next point I want to come to, sort of the practical backdrop to the case study and some of the other comments that I have here that I want to share with you. In the last 100 or more years, we've developed economies, we've developed land use patterns, we've developed consumption patterns that really require highly centralized generation and distribution of power, of electricity to a very large extent. Now with climate change, one of these tightening constraints, we recognize serious limitations in some of the centralized power generation, which is highest during hot summer months, which will become more frequent, increasingly hot. And we oftentimes now find that for nuclear power plants, for example, we need them most just at the time when you can use them least, because of reductions of cooling water availability and the like. Or in the case of coal-fired plants, it's not just water that's needed to cool them, but it's also ambient air quality standards that might be surpassed. So just the time we need them most, we have them least available. The same actually holds for transmission efficiency and generation efficiencies, which are lowest typically during those peak load periods, which also adds another set of challenges. And if this holds for the hot part of the year, similar challenges happen during the cold part of the year, when downing of power lines during winter storms are really now becoming increasingly the norm under which we need to operate. And some of you might have experienced this at times. And it really leads to serious challenges, not just for the local utilities, but also serious challenges for the people who rely on power. With, and this is unfortunately a little hard to see in the resolution here, but with then oftentimes very large-scale outages of power for entire regions, to some extent, if they happen for longer periods of time, really undermining the economic profitability of the businesses, the health of the population, and the like. So we've sort of locked ourselves somewhat in to this kind of setting. Now you go to ecological economics and you hear, among other things, that we need to transition, obviously, out of this fossil-based energy, highly concentrated energy system into one that's using renewable resources. And so one of the key questions is, how do you actually make the this transition happen? And I want to get back to this in a minute. But then there is, aside from the impact of climate change on the energy sector, there is obviously also the emissions side to this. And what you have here is sort of a list of states in the European Union and in states in the United States. And you'll recognize that many of these states are actually, in terms of their carbon emissions, right up there with many countries. Within the EU, the state I'm living in now, Maryland, comes ahead of Norway and Denmark in terms of its carbon emissions. So, worldwide, we are among the largest energy consumers, the largest emitters of carbon, but also at a regional level, we really do play a major role on the emissions front itself. That said, when it really comes down to the regional, in this case it's an aerial photograph, or actually a satellite picture of Baltimore, where I've done some work on climate impacts and health, public health issues in the urban setting. Whole new slew of challenges to local decision makers and planners. How do you deal with the impact side and then the emission side? And here the emissions really oftentimes manifest themselves in terms of low ambient air quality. And so what you have here, the darker the red, it's actually the healthier the urban vegetation. And then if you look at, so this is again so roughly the same area, Baltimore, where the poor, the elderly, the people with health problems are located. If you combine those two, you sort of get very clear hotspots within the urban environment where climate, urban heat island effects, and air pollution really come together to affect quality of life in very tangible ways. Decision makers at the state and urban sort of regional level are now grappling with how to deal with this. I mean, they are very individually all very small players on the climate change front. I mean, it's nothing that Baltimore can do to affect the climate, right? There is a lot that they can do in order to help the populations deal with those issues and prepare themselves, and also then sort of meet their mission of becoming more responsible players on this global scale of carbon emissions, or greenhouse gas emissions in general. So what we find, and that's really all I'm trying to say here, what we find at this local and regional scale, at the urban to state scale roughly, that climate change, one of these tightening constraints really sort of functions like a threat multiplier. Already crumbling infrastructures, already underperforming infrastructures and social services and institutions don't work any better now when you put the climate signal on top of it. Or another way to put this is already existing needs for these goods and services increase because of some of the tightening of these constraints. And so how do the states, and now I'm talking a little bit more about Maryland, but this is really just meant as an illustration. How do the states prepare themselves to deal with this? How do they sort of take this head on? And Maryland is one of the states that has started to take this on very aggressively by developing climate action plans. And I know here in Vermont there are also there is at least some talk and some small initiatives starting to sort of get a handle on the mitigation side and to some extent on the adaptation side. How does Maryland do this? How do many of them do this? Well, looking at the climate challenges through these other sort of threat multiplier impacts, the social, the environmental, the infrastructure related issues, and really trying to harness, co-benefits that can come from implementing particular strategies. And so we're really trying to now reshape at the regional scale the way in which institutions work and the way in which we do business, the way in which we invest in infrastructure, the way in which we invest in education, the healthcare system, and so on, but keeping in mind what's coming ahead from the climate and other environmental drivers. And so trying to find these co-benefits so that we don't have to spend $1 and spread it over all kinds of different outlets, but spend it one and get multiple of these bangs for the buck. That's sort of the goal. What does this all mean for ecological economics? I mean, from my perspective, actually one of the things this does is to provide a whole new playing ground in which we sort of, as ecological economists, haven't really played yet. We have a tightening of these sort of biophysical constraints. This is something we've talked about all along. But we are now also very actively reshaping the way in which we do business, in which we invest in infrastructure, in which we basically lay the footprint for future development of an entire region. So that adds another whole slew of uncertainties and surprises into the equation that we really need to deal with simultaneously. And so there's a wonderful opportunity that's already recognized at the policy decision realm, and for which we have already set a set of tools to analyze the respective issues and provide input. And so, here's one way to do this. But there are also very clear challenges of doing this, and I want to just spend one more minute on some of these challenges before I sort of go off on a little tangent called case study and then come back. A large amount of money these days is spent, a large amount of money has been spent on refining ever more the climate models on which we try to make decisions, to the point where my climatology colleagues now can tell you something about roughly the probability of the occurrence of a particular kind of heat event during the afternoon hours in a relatively small segment of the state in the year 2048. We're trying to use this to guide policy with data on population dynamics that comes from the census that we do every 10 years, with economic information that's typically a year old, with data on energy consumption that's collected from different deregulated utilities, where we lump all the energy sources together annually, averaged per household or per inhabitant in the state. These models don't zipper up. They don't. The data and the perspective on how to really move decision forward. It's not there yet. How do we develop these synchronized models where the two pieces of the equation really go hand in hand? And so we really need to beef up the economic, the ecological, and some of the other insights to match with what comes from the physical models, for example, the climatology models. Another thing that we find at the local level is that sort of what we refer to in economics as marginal analysis, a little bit more of one thing, what's the impact? It doesn't really work all that well. I mean, you either build a power plant or not. You either commit a few tens of millions of dollars to an initiative or not. So they are oftentimes very binary decisions for which we need a different kind of analysis, at least at that level, from the ones that we typically have carried out. And then last but not least, and this is sort of the obvious, that we're sort of, I think, pretty good at sort of dealing with uncertainties and risks. It's much more difficult for us in these complex environments to deal with fundamental uncertainties. And modeling to some extent can help at least shed some light on this. So from the theoretical perspective, to sum this up very quickly, what we need are approaches that are consistent across the different disciplines that come together and sort of provide a holistic perspective on an overall system and its dynamics. And then from a practical perspective, we sort of begin to realize that of the internal dynamics of the social and economic systems in particular locations where those decisions ultimately need to be made, and the outside influences, be it climate or globalization or demographics and the like. So putting those two pieces of the puzzle together, an interesting intellectual challenge to say the least. And to some extent, this is something that ecological economists might want to venture into. So step back for a minute, and there's a little bit of political context to this as well. Many states around the U.S., Vermont, one of them, trying to promote wind power as so one of the alternatives to the fossil fuel generation, in part because it's green, it's carbon neutral, largely so, 100%, but it's largely carbon neutral. But also it is to some extent less susceptible to these disruptions in the supply chain of the fuel cycle. Like if you think about cooling water supplies to power plants, if you're thinking about disruptions of oil and gas to power plants, wind turbines, once they're up and running, they're up and running. So they are not just a mitigation strategy, but to some extent they are also now increasingly perceived as an adaptation strategy, adaptation to some of these outside influences. Okay? But it's not conflict-free, as we all know, especially if you want to do this on land. And so coastal states, this is not an issue particularly for yet, maybe with enough sea level rise, but it's not an issue for Vermont. But many states now really push very hard on offshore wind. And as a matter of fact, I work very closely with the Maryland Energy Administration and the governor and the governor's office. And yesterday afternoon, there was a press release by Governor O'Malley in Maryland that he plans to very heavily invest in offshore wind as one of the biggest drivers to revamp the energy system, to make us less susceptible to some of these disruptions and also do right by climate change. So I want to talk a little bit about that, but particularly some new kinds of conflict areas. All this is part of the Regional Greenhouse Gas Initiative, which actually the center that I run, we sort of helped create and help Maryland to become part of this. It's a cap and trade system where we limit emissions of greenhouse gases, and then basically through legal instruments and economic instruments really try to improve the environmental performance of one part of the power sector. But also many states like Vermont have renewable portfolio standards here. The expectation is to have 10% of the power generation to come from renewables by the year 2013 in Vermont. Maryland, it's 20% by 2022, so annualize it. Most of the states that do this do it very, very similarly. And wind plays a major role in this, okay? And particularly offshore wind in the case of Maryland. I don't want to talk about impacts of building these offshore wind parks, if you wish, out on the ocean on ecosystems. There's sort of a companion study I've been involved in that sort of deals with this, and it's all sort of pretty straightforward. And we can later on question period, we can get into that. There's sort of the public perception piece to it. No one wants to have a windmill in their backyard. If it's 20, 30 kilometers or 80 kilometers out on the ocean, it's a little bit less of an issue. So public perception, let's put that to the side. A really interesting one, a somewhat ironic relationship is with national security. There's this big push to decentralize and localize our power supply so we become less reliant on fuel supply from elsewhere. And so green energy, to some extent, is pushed as a strategy to, as part of the energy security strategy of the nation. Well, at Maryland, like most other coastal states, the military actually has a very large presence on the coast. So what we've done to start was to figure out, should Maryland move into offshore wind? How much should they move into this, and how much can we get actually from it? That's sort of one of these questions we try to answer. First thing we did is, so here's a bathymetry map, off the coast of Maryland. So it's Delaware up here, Maryland down there, and then Virginia, Pennsylvania out this direction. So what you see, this one wedge here, is part of a very large Navy exercise range where you would not want to put multi-million-dollar investment in the way of the missiles that they test and the fleets that they operate there. So I want to sort of block this off to start with. There is Wallops Island, where NASA launches rockets and satellites, and so there are flight paths that you cannot interfere with, so you take those out of the picture. And then you look at the various radar installations that are used for weather monitoring, ship movement, military activity, and the like. And you can calculate what's known as radar line of sight. It's basically how far away do you have to be from the radar equipment to not create Doppler effects and all kinds of other interference. And that obviously depends on the height of the equipment that you put there. And so these are the lower towers that are only about 130 meters in height, all the way to about 189 meters. These are sort of the larger pieces of equipment. So the larger the equipment, the further out you have to go. So there's really not a lot of ocean area that's left under those constraints. Those constraints can actually be changed, and we're sort of currently working on trying to change those. But then, with that little area, it's not that little, but with that little area, then the next question is, how do you connect up to land? And so what you see here on the left-hand side is the existing grid infrastructure to which you can connect different kinds of power generation of offshore wind to the market, basically. And the next one sort of zooms into this a little more. So what we've done is fairly detailed analysis of the congestion environment within which wind energy needs to come on shore. Where are the transformers, where are the substations, what are the different lines, at what kinds of voltages that help you sort of connect up to the rest of the grid. If you take that all into account, that sort of shrinks even further the solution space that you have available to bring offshore wind online. Now, the next thing then to do is to figure out actually what kind of wind farm you want to have. And here's a little illustration for one of the options that really only sort of are left at the end of the day. One is a 600 megawatt offshore wind farm that's 27 kilometers out. And then you go through all the different cost components that you would need to build this up based on experience from other investments of this kind. How many monopiles do you need, what kind of switching gear do you need. So we basically, quote unquote, priced out this package that you could put in place there. Okay? And then, we've done this also for 1,000 megawatt, deep water, 80 kilometers out from the coast, operation, have all the numbers to go with that as well. And the next step in the process would be, say, hey, we want to move towards offshore wind. Now, what's really the energy production annually that we can expect from this? And so in a simplified way, it's really a function of what the design is like, a 600 or 1,000 megawatt operation. The capacity factor really is very largely a function of the wind speed in the particular locations that you have available and the configuration of the turbines within the wind farms. And this is data that actually the capacity factors nowadays come from experiences of operations in Europe, but using very local wind data that comes from NOAA weather buoys that are out there in those places where we want to put the wind farms. So this is all sort of localized information. The availability will sort of leave somewhat constant here, 95%, so the other 5% are downtime because of storms when you actually have to shut the equipment off, or the wind's not blowing enough, or just ordinary sort of maintenance and upkeep. Then the next thing you want to do is sort of cash flow analysis, annualize all these different costs and the revenues that would come from operating these two different kinds of wind farms. And we don't need to go through all the details, but it's like issues of cabling. You have to pay to the mineral management services, which is part of USGS, you have to pay lease costs, and so you can sort of calculate this out, and you actually find that for both of these investments, there is positive return on investment, and they both have sort of payback periods under 10 years. So after, within 10 years, they both paid for themselves. So both of them seem economically viable options, right? Great. Next step is that obviously, the cost and revenue stream sort of are temporally, structured. It takes a little while to get the first turbines going, and then based on your finance instruments that you have available, you want to plow back some of the revenues that you generate into an expansion of the wind farm until you hit the 600 or 1,000 megawatt. And so what you see here is sort of the cutoff period, assuming we had launched this in 2010, the smaller wind farm by about 2017 or so would have sort of had a break-even point, and then from here on out, revenues exceeding the cost. And it happens a little earlier in the larger operation. But then the next really interesting question is, how does obviously all of this change given alternative assumptions about energy prices, about equipment costs, about discount rates, all the things that go into these cash flow analyses. And this is a result of over 2,000 Monte Carlo simulations where we sampled within the ranges of the various cost components, the wind speeds, the downtimes, and on, particular portfolio constellations of parameters. And what you see here, these are the standard deviations in parentheses and the mean values. So under any of these historically observed differences in prices and so on, both of those operations would be profitable. Right. How much power would wind then, being profitable, replace power that comes from traditional energy sources like pulverized coal and gas-fired power plants and the like? So, we have a few of these. There's a PC plant, there's a natural gas combined cycle plant that are already under operation, and the expectation would be that some of that power gets replaced by wind generation. And so in order to know how much actually gets replaced, that's so very much an economic decision-making process, and what you bring online is the power source with the lowest marginal cost of generating, in this case, the electricity. And so you need to actually go through the same kind of exercise to calculate what the cost profiles are for any and all of the other alternatives. We've done that. And so just to sort of cut to the chase here, so this is the natural gas combined cycle plant operating over a range of different hours during the year, and then the associated cost of generating that power, so the pulverized coal plant, the integrated gas combined cycle plant, and then here are our two sort of the offshore wind operations, the 27 kilometer out smaller version, and then the 80 kilometer out larger version. And sort of within this range that the displacement takes place. I actually have a graph that looks maybe a little better than this. So here is the average efficient cost curve for power generation based on the portfolio that we have available. And here is sort of the contribution that offshore wind can make. And it's really within this range that we're replacing from the traditional sources, which amounts, under this range of parameters that I mentioned earlier, amounts to about 0.8 to 1.6% of the energy consumption and roughly that much of the carbon emissions. Not what I necessarily would call a revolution in the energy sector for the state. And so, what are the lessons that we sort of take away from this? Coming back to some of the institutional issues and the other boundary constraints that I mentioned earlier. First, all but one of these can be changed, and as a matter of fact, that's exactly what we're engaged in right now, working with the state legislatures, actually working with individual companies and trying to figure out, not just, and that's what we've done all along, what to do with wind, but in order to make wind successful, you actually got to touch the entire energy system, the entire portfolio of the state, and change the incentive structure under which they operate so that wind actually has a chance. And it's more than that even. It's revamping the entire energy grid within which you want to feed in, and everyone else already has dips on how that gets expanded based on the traditional energy sources. So it's a major rethinking of the way in which the energy sector and the state will function. The other thing that we've learned is, and that's the obvious, there is no silver bullet right? Sort of my first experience dealing with a decision making. Oh yeah, what's the solution, right? Should we do wind? Should we do solar? Should we? There is no silver bullet. What we really need is sort of silver buckshot. There's lots of different ways of attacking the problem from all different sides. But you laugh, but there's a serious intellectual challenge doing this because we don't really have the portfolio decision-making tools available that get at these systematic issues that we really try to change. Right? And so there's a nice role here or elsewhere, for a research center, for an education center, to sort of create an approach to how to think about these very large, complex systems in new ways, so that we don't always just look, for the one solution that we already know won't make a big difference. And in order to get to this point, it really requires also that we have a different way of measuring system performance. And again, the first time when we were asked to help with a regional greenhouse gas initiative, the first question was, what's the impact on the economy of the state? Will it continue to boost, economic activity and jobs? And these are all laudable goals, but they also, to some extent, especially boosting economic activity, they undermine some of the progress that you might make. And so the fundamental restructuring and the rethinking of how we do business and what kind of business we want to do, that's really just now being kicked off. And as a matter of fact, Governor O'Malley appointed a group of 6 people, very select, to help think about what it would mean to have a sustainable Maryland. There's a lot of talk about this, but this guy seems to be quite genuine about it. And it's everything from alternative measures of economic performance and social and environmental performance like the GPI and things of that nature, to much more fundamental ways of structuring the agencies and the way they work and the incentives that are available to them to change what they're doing. So that's sort of one challenge, sort of this, get a system-wide perspective of how well we actually are off under all these different strategies. And really sort of the rest of it is a bit jargon, but what we want to do is, through time, want to know how we perform, not just at a point in time, and also across space. And if you wish, could add into this across social groups, for example, across environmental media and on. So with this, I really want to come to a close, the promised 35 minutes. I want to reflect a little, and I've hinted at this, on sort of what the role could be or should be of a university in all of this. Universities, unlike consulting companies, and I don't mean to speak negatively about them, I've worked with a lot of them and I enjoy that collaboration, but it should be driven by sort of intellectual curiosity and have a certain integrity in the way about which they go about doing business, the way in which we analyze issues, and that should carry the day. And I think we always need to sort of remind ourselves of that. It's not Gund or whatever it is, or the center that it's not a consulting company in a university. It's an entity of a university that happens to do, hopefully, meaningful and relevant work. And coming back to sort of my interpretation of complexity, you can't do this by just sort of drawing on one particular discipline. You have to have that pluralism, that diversity. And if we don't have that, the solutions that we offer are equally impoverished as the tool chest and the team of people that we bring to bear on these issues. So diversity is really key, and the integration across all the different parts is really key to success. It's not just rowing them up like pearls on a string. And then I firmly believe that, and you sort of already do a lot of this, use the campus as the laboratory for the sum of the work that you do. Think about your energy consumption. Think about your energy supply system. How do you want to structure this? Green buildings for the urban. All these kinds of things are really an integral part of changing the culture in which we think, in which we work, and hopefully it sort of has ripple effects that go well beyond the institution. And I've said this on a few conversations I have during the day. You're in a really good spot here. 25 years of ecological economics sort of have passed. A lot of the dust has settled. You are at a place where you can define where it's going to go for the next 25 years. That's an interesting challenge. That's a great position to be in, and you've got much of what it needs to be there and really own it You already got it here on campus, and that's really great. With this, I want to just leave it at that. A few pictures here, and if you want to know more about some of the work I've done on industrial processes and sort of industrial systems analysis, or it's hard to see, but sort of urban infrastructure and planning and land use planning, or nutrient issues surrounding managed ecosystems, decision making under risk and uncertainty, the distributional impacts of climate change and climate adaptation, and not just change, but also the policies that go with it, or then ultimately, using one's own campus to move towards carbon neutrality and to adapt to climate change. Be my guest, check out the website, send me an email, or even better, ask now.